My name is Wale. My Twitter handle is Wale Akinfaderin, so you can always tweet me if you have questions about this talk. And I'm going to be speaking about the creative art of engineering bespoke features. So this is mostly a feature engineering talk, and I try to make it also very beginner-friendly. For my talk outline, I'll be introducing myself, then also introduction to sort of feature engineering, and then I would talk about feature engineering for mostly categorical features, numerical features, datetime, and coordinates, and other techniques. So I will be focusing on structured data sets and not on unstructured data set like images and text. Okay. So a little bit about myself. I'm currently a data scientist for a giant retail company in Charlotte, North Carolina. Before that, I was a physicist. My PhD research was in magnetic resonance spectroscopy. And I'm sure you guys are wondering how I went from being a resonance spectroscopist to sort of a data scientist and a machine learning person. So during my research, I think it was in my third year, I was mostly doing experimental physics. So that means I get data, I build instruments, then I get data from the instrument, but I also need to make sense of the data. So that means I have to do maybe some exploratory analysis or some data analysis then using MATLAB. And I really enjoyed that part. And that was how I actually got into machine learning. And I noticed that machine learning and data science was a path for me to sort of make a much broader impact. And I've enjoyed it since then. I was an Insights Data Science Fellow. If you know about this fellowship, I think I really recommend it. It's really good. And also before that, I spent a summer at IBM Research in Nairobi in Kenya. So I enjoyed, I went on safari a lot, and I hiked, and I did some work. So I was doing mostly machine learning for development, looking at data for NLP, and just trying to use machine learning and natural language processing to sort of look at safety procedures in East Africa, and I enjoyed it. And so one of the things I've been really interested in is democratizing machine learning, and that's why I'm at this conference, and I'm enjoying it so far. So I really like soccer. I've heard about the Portland and the Timbers, that they're good. I like playing Scrabble. Okay. So that's me in a nutshell. Then I go straight to the introduction. And so a lot of us do machine learning, and I remember the first time I saw this code from Andrew Ng that says that machine learning is basically feature engineering. Applied machine learning is basically feature engineering. So that means at some point you build your machine learning model and you have some sort of baseline that you set, but you also want to get better. Most times it comes back to you doing feature engineering. And then this other code that says more data beats clever algorithms, but better data beats more data. I think I really like this code, but I also think this applies more to classic machine learning algorithm. I don't think you can say the same for deep learning, where your sort of model accuracy scales better if you have more data. So this is just to prepare us for the talk. And so feature engineering, in most cases, is just a process of introducing knowledge into a machine learning model. So that means you sort of have a machine learning model and you want to improve on it, and you find a way to actually introduce this model. And these features are actually variables that you find in this given problem set, and you can actually use them to build accurate and predictive models. So the knowledge that you're introducing into this machine learning model, they're actually these features. So they represent the appropriate knowledge for machine learning algorithms. So this is a machine learning conference, and I have a slide on what is machine learning. So mostly what you do is you have these two parts, which is the learning part and the prediction part. So that means you have an existing data that goes through your algorithm, and you have a trained model. And normally what you do is then you take new data, which sometimes can be your test set, and you actually take it, go through this sort of trained model, and then you have your prediction. And in this case, like I mentioned, we're actually looking at sort of structured data. So your data in this case will actually be several vectors of length d. So if you're dealing with images, for example, then you have to talk about tensor and things like that. Okay, so why feature engineering? Engineering good features is actually really good. It allows you to most accurately sort of represent all the underlying structures of the data and the interactions between this structure. And therefore, you can use it to create the best model. Also, the features in your data will influence the results that your predictive model can achieve. So that means you want to get it from point A to point B, then feature engineering is important. Also, for sort of every good thing, they also have their limitations. And feature engineering has its limitation. For some data sets, like let's say healthcare, for example, like a clinical trial data set, that actually you have very small data. Sometimes it's a little bit difficult for you to do feature engineering because the degrees of freedom becomes very thin if you have small data sets. And also, if you include too much correlated variables, you can actually decrease your model performance, because at some point, if you have, so your P is actually your number of columns in this one, at this point. So if you have too many variables, it's very possible that some of them might be correlated, and then you have this large P versus N problem. Also, more variables can actually make the model less interpretable. So I've actually seen a lot of arguments about interpretability and explainability, such that sometimes it depends on your model. So that means if you are running some sort of extreme gradient boosting or a deep learning model, then it's sort of not an interpretable model. But also, you can actually run a simple model on a really large data set with a lot of variables, and it will be very difficult for you to interpret. And also, sometimes feature engineering is sort of between the interpretability accuracy trade-off. Do you want a much more interpretable model, or do you actually want to improve the model accuracy or the metric, and you don't really care about the interpretability? And sometimes it's also difficult when you feature engineer for you to generalize the model to other data. Is there anybody from New York here? Okay. Oh, that's amazing. A few years ago, I actually came across an artist in New York. So his name is Jean-Michel Basquiat. He was from Lower East Side Manhattan. He was a fantastic artist, but also he was very eccentric. And I was looking at some of his artwork that I think there was one that sold for probably $100 million. And it was really, I was shocked. So then I started looking at him and just sort of studying his works and looking at his creative process. And some of the things I've seen is that he does a lot of planning. So because he started as a graffiti artist, so he plans a lot. He knows where the site is, where to sort of paint and things like that. Then immediately after the planning, he actually goes to create and improvise. Then he reviews and revise. And also, part of this review is for him to actually refine his thinking. So by sort of interpreting some of his artwork and explaining to people, then eventually share and reflect. And I think he died in 86, and for 6 years of his life, making like really great artwork. It was very consistent with this process. And that also brings me to the creative process of engineering features, right? The first thing you want to do is actually want to define your problem and plan. So is it a prediction model you're trying to build? Is it a recommendation engine? Also, you want a thorough understanding of your data and your model. So you need to do some exploratory data analysis, of course. So that means you need to do summary statistics. You need to understand the probability distributions in your data, and also the model assumptions. So I think this is really important. Like every model that you use, it's always good to know the assumptions because they actually help you engineer better features. And then you also want to plan your feature engineering goals. So are you trying to optimize to make your machine learning model faster, or are you actually trying to improve on your performance? So that means if you're running a regression model, do you want to improve your RMSE or your F1 score? So what exactly do you want to do? Then after that, you need to refine your thinking by interpreting and explaining. So in this case, you interpret, you test, you iterate. And you keep on doing that until you get better. And so this is actually the creative process of engineering features. Okay, so like I mentioned, I was going to talk about mostly features with structured data set. So I'm going to start with categorical features. So categorical features, in most cases, they actually need to be engineered. There's actually no two ways about it. And also, but one of the things that you see is encoding categorical features can lead to sparse data if you have very high cardinality. And also, it's actually a little bit difficult to impute missing data because they easily lead to an over or underestimation of variability. So what I'm saying is if you have some sort of structured data set where it's a continuous variable, and you're trying to do some missing data imputation. In most cases, what people do is that they can actually just use some measures of central tendency. So that means they actually want to encode using the mean or the median. In most cases, you see categorical features, and they actually use the mode. And when you try to look at it, it's actually really just go above what the normal variance is or reduce it. So it's really sometimes difficult for missing data imputation. So the first one I'll be talking about, which is the most common one, is one-hot encoding. So this is really common for nominal categorical features, and it's actually easy to explain, and sometimes the results are really easily intelligible. This is really a made-up data set that I made up. There's nothing. And so this is just data that has a car table, and you have the car manufacturer. So it could be a Honda, a Toyota, a Ford, and a Mercedes. And also you have this miles per gallon for the car. And so when you do one-hot encoding, you take each of, so the feature, which is the categorical feature, in this case is the car manufacturer. So you take each of them, and you actually one-hot encode. So that means you have like the Honda, Toyota, Ford, and Mercedes. You have them in sort of like a one-dimensional vector, and you have one. So you encode a number where you see Honda, and you could see Toyota has 01100, and also you could do the same thing for Ford, and then the same thing for Mercedes. So one-hot encoding is great, but also it has a lot of drawbacks. Sometimes you could have too many features. Then it becomes computationally expensive to train complex algorithms. Most times actually limited to non-tree-based models. So non-tree-based models in this case are sort of linear models, linear like regression, logistic regression, and also sometimes deep neural network. Because you sort of have, you could have like really many features that you've created, and then you really need larger memory because of sparsity. And also there's a possibility of multicollinearity where you have like two or more features with very, very high correlation coefficient. In most implementations that I've seen, I think on scikit-learn, I know that they actually don't really treat missing variables. And so those are some of the drawbacks. This is actually one of the very straightforward one where you do label encoding. And in this case, you just assign a numerical variable for each level of category. And then sort of what you do is when you assign that, you assign natural ordering between the labels. And it's actually good for both. You only have the tree-based and the non-tree-based. So the tree-based, they are from the decision trees to the random forest, just all the ensemble methods. And in this case also, you have a constant dimensionality. So that means you're not you're not making the Honda, the Toyota, and the Ford new features right now. So you also have just the same dimensionality in your project. Okay, count encoding, this is a little bit straightforward where you just change the categorical variables with the number of counts for each variables. Sometimes when you have something with so much count, it could be sensitive to outliers. And so and also because in this case where you have Honda, Toyota, you have Ford, Mercedes, and Honda, they actually count as one. So there could be some unwarranted interaction between them. And so, and also if you have like a skewed count, you could do maybe a log transformation, which I'm going to talk about later. So this is label count encoding, where what you do is that you count the categorical variables, and then you rank by the number of counts. And it's also good for when you have like tree and non-tree based methods. So let's say you have a Toyota, which in this place you actually can count it 4 times, and you can easily then you can rank it as number 1. Honda actually appears twice, and you can rank it as number 2, and you can also do the same thing for Ford and Mercedes that appeared once as 1. Target encoding, this is actually one that I really like the most. And what you do is in target encoding is you take the categorical variables and you encode them using the ratio of their target count to their variable count. Sometimes it's a little bit tricky because you could have some sort of possible correlation between the encoded feature and the target, and it's really good for large number of features. And actually, if you do a lot of cargo competition, this is really one of the good secrets from top car glass to win competitions. And sometimes what they do is they try to add some random noise to combat overfitting. So this is sort of how target encoding works. So you have under, and if you count it, it's actually 3. The Toyota is 5. Now, let's say, for example, you have, this is a data set from a car company, so a car rental company. So they're trying to find out their target variable is if they should buy this car or not. So 0 is yes, we're getting it. 1 is no, And so it's for binary classification. So you could see that 1 actually appears once out of the 3 options we have for under, right? So the feature target in this case is going to be 1 divided by 3, which is 0.33. And you could also do the same thing for Toyota, which actually appears 3 times, and 3 divided by 5 is 0.6. And you could actually do that for all your features for target encoding for binary classification. You can also do it for multi-class classification. Okay, so the next step is numerical features. And so numerical features mostly are continuous numbers, and one of the easiest way sometimes to handle them is you want to bin. So that means bin is you're converting a numerical variable to discrete variable. So that means you do this conversion by declaring a range of values. You could actually sort of do that by trying to find the percentiles, and you could use that to do the binning. And you could have like a fixed width binning. So the image below is an example of a fixed width binning for some set of numbers, randomly generated numbers from, I think, -50 to 450. Rounding. And so one of the things you want to do when you're trying to handle numerical features is that you want to keep the information. So rounding actually helps you to keep the important features of the data. And also it can help you remove random noise. So for example, you could have some data where, let's say, you have decimal places in like tens of thousands or so, and you actually want to remove them. So, and also you can use them to form categorical variables. So this is miles per gallon from the data I showed, and you have like 23.2 and all the numbers. You could actually round it like this, or you could actually just pick like the first number. And in this case, you'd have categorical variables. And this is a really good method to actually generate new features. Another thing is scaling and normalization. So in some cases, you have a lot of data from different range, and you actually want to try to scale and normalize them between 0 and 1. And these are some of the useful ones. So you can scale min-max value to sort of scale towards the mean, where you take the value y minus the minimum of y divided by the maximum minus the minimum. Sometimes also you actually want to keep the outliers. You don't want to really lose the impact. So in this case, you could use like a z-score scaling, which is where you subtract the number from the mean, and then you actually divide by the standard deviation of your feature. And also, there's this logarithmic scaling where you calculate the log of the values to narrow the range. And also, this actually changes the distribution, and in most cases, and I think in the last talk, we actually heard about some of the performance of ordinary least square models, or not some of the assumptions for ordinary least square models. So it actually improves it, especially if you're trying to normalize data. Then the next is I'm going to go to label engineering and transformation. And so I wanted to talk about logarithmic transformation initially, but I thought it was better for me to talk about Box-Cox, because the Box-Cox transformation, these power transformations are sort of, the logarithmic transformation is a family of Box-Cox. So this is, I think it was introduced by 2 statisticians in the 60s, where they developed this transformation for removing heteroscedasity in the feature. And so heteroscedasity in your data means you have a lot of these features, and their variability are different. And you want to find a way to actually make them the same and try to make them normally distributed. And so you could, and this transformation is performed by sort of running an experiment to find the accurate lambda value. But when lambda is 0, the Box-Cox actually just becomes a straight logarithmic transformation. And so it's really good for you for selecting a transformation for linearity or normality. But one thing you would see in this Box-Cox is that when your y is negative, it becomes really, you can't use it because it's actually restricted to positive values of y alone in your data set. And then it brings me, so this is what sort of a Box-Cox looks like when you have like a before data and after data, and then you could see that now you sort of have like a reasonably normally distributed feature. Okay, so the next thing is something called the Johansson transformation. And so this is very recent, probably, I don't know, in statistics recent, it's probably 18 years ago. And so the box cox is restricted by the value of y. So what this transformation does is that when you have your numeric features and you have a lot of negative numbers, right? So it's actually a new family of transformation that you can use without placing any positive value restriction on your y. So that means if you have both positive and negative, you can actually use them. And you could see from the old maths equation, you could see when y is less than 0 and when y is greater or equals to 0. Actually, I've seen an implementation of box cox on, I think, I can't remember, maybe stats model, but I just noticed that I've actually not seen any of you, Johnson and Python. So hopefully I'll probably write one very soon. And so the next is dateline and coordinates. So in most cases in your data, you have like time series data, you have date and time, and you actually don't know how, you want to find a way to actually encode these variables. And the first thing is you want to look at the periodicity. So what's like the day number in a week? Is it a Monday, which is probably if you start Monday as 1, or is it the 10th of the month, or what day of the year it is, or what's the season? So periodicity is always good. And then also time since a particular event. So you could actually encode, try to get sort of popular holidays. So is it the Christmas or Thanksgiving? You could actually sort of look at the number left onto recent holiday. Or you can just pick a random date and try to find the difference. And also you could do the difference between dates. So that means you have like a feature 1 and a feature 2. So for example, let's just think of this hypothetical data of house prices. You want to predict house prices in the Portland area. One of the things you could get public data from Zillow, for example, that shows maybe when maybe some house is listed and also when it was sold. You could actually then take the difference between the time between being listed and being sold, and you could use that and encode it into your date time features. Coordinates are really good. Sometimes for this, you would do clustering algorithm like KNN for you to find center of clusters, and you could encode that. And also, you want to do like distance to the nearest point of reference or major hub. So, for example, you want to find what's the distance. If I'm thinking of the Portland house data set, you want to find the distance between some house to downtown, for example. Maybe the closer it gets, the more expensive it becomes. And another thing is aggregated statistics. So you could take Hillsborough, for example, and look at the prices of houses, and also you want to do aggregated statistics from, let's say, maybe some social demographic data, or you want to find what's the median salary range in these places. And you actually want to use that to encode that for coordinates. For tree-based methods, sometimes including a feature that describes how you rotate the longitude and latitude is actually very useful. I've seen that, and it actually gives you very good predictive performance. So in this case, so let's say you have the latitude and longitude, and you have the high price district on one part, and the low price district, you could actually do different rotations. So you could actually rotate by maybe 45 degrees or 90 degrees, and actually encode all that into the data, and it gives you really powerful predictive performance. So the last technique we'll talk about is encoding nonlinearity. So sometimes you could see the green and the red. They're linearly separable. It's very easy. But sometimes you actually see them that they're actually not linearly separable. One method that a lot of people use is actually maybe support vector machines. But also you could use something called feature crosses. And feature crosses is where you create artificial feature, and you can actually apply two or more input features together to encode this linearity. So that means in this case, for example, you can create a feature from x1 and x2 that I showed, and you could create new features, so maybe a product of the feature x1 and x2, or x1 squared. And this newly created feature, you actually add them to the linear model formula in this case. The only downside is sometimes it could actually be computationally expensive when you're trying to train them on linear models, but the stochastic gradient descent actually makes it a little bit efficient for you to train them. I think finally I leave you with this again, which is actually the creative process of feature engineering, which means you want to define your problem and plan. You want to know if it's a prediction or a recommendation. Also, thorough understanding of your data and model is very important. Planning your feature engineering goals. Are you optimizing for speed, or you want to improve your metric performance? And also just refine your thinking by interpreting and explaining. And this is actually a little bit similar to the process of Jean-Michel Basquiat that I mentioned before. So I want to say thank you.